I did prepare a presentation. It's the basic coastal processes, so we can get all of us on the same page in terms of what are the issues, and these are just food for thought in terms of as we begin to think about what living shorelines for specifically in Connecticut is. A lot of this is going to give us the ammunition and then the really understanding of the basics, Mother Nature, what she can do, and then as we progress into defining what living shoreline is. This reminds me why we choose to live near the shore. It's a wonderful picture to start with. When I think about coastal processes, when I started my career, we didn't talk about ecology as much. We talked about hard assets, coastal structures, sedimentation, and then we dove into it. But as we got into the lateral part of our life, our senses about what the coast is all about just changed and matured. And then we began to take a look at the coast as a total picture rather than individual actions and events. And then that's how I really usually approach any project that I usually do. I first try to understand the atmospheric events. Jennifer talked about it a little bit. What really creates the coastal process? It's winds, waves, hurricanes, nor'easters. Then after I understand that, I begin to assess the coastal hydraulics. That transfers into waves, currents, tides, all that stuff. We have to assess that. We need to understand that. Then we move into coastal sediments, the softer stuff, the sand. It plays a big deal in terms of how we protect ourselves and how we transfer our knowledge from offshore into the coastal areas, into the inland estuaries. Then we get into coastal structures, typical engineers. Let's build a big breakwater, let's put a big wall. We have the technology, we can do that. Yeah, we did that in the past, and then some of it is good, some of it is productive, some of it is not. And then today we get to really look at that, and we want to migrate from the very hard structures all the way to the soft, and I call these bookends, and how we do that, how we combine them together in a hybrid system, given the type of energy, the specificity of the site that we are dealing with. Then, of course, we get into coastal geology, which really completes the entire loop for me in terms of understanding the entire process. What influence the coastal processes have? Hurricanes, nor'easter, winds, and waves. Again, Jennifer touched a little bit about it. I'm going to take you into a trip a little more in-depth into it. The above are created in a basic process, which we call the rotation of the Earth. And then that's what creates the winds, the moves from east, west, south, all of the other stuff. And with that, let us examine every bits and piece of that and see how we want to deal with it. Here's a powerful hurricane. Their characteristics are very simple. The common season on hurricanes is usually July to October. They form over the oceans. They move north to south to north. They're usually associated with huge low pressure, have counterclockwise rotary movement in the northern hemisphere. They have a distinct eye in the middle, which sometimes could be as big as 20 miles long. And then as the eye shrinks, the hurricane intensifies. I think it's important to know that. And then, of course, they generate very huge damaging winds. And usually we move from tropical storms to hurricane category when the winds begin to exceed 75 miles an hour. And diameter of these hurricanes can range as small as 75 miles to 1,000 miles. Sandy was one of those hurricanes, had almost 1,000-mile diameter. Little joke on the side. When I was going to college, I had a girlfriend, her name was Sandy. I know she was troubled then, and then 38 years ago, she proved herself that she's still a trouble. Hurricanes around the world. I wanted to give you an idea that hurricanes not only just happen on the East Coast, they happen throughout the world. In the Far East, or we call them typhoons in different areas. You can see the concentration of these cyclonic really events, it's influenced by the equator. It happens north of the equator and south of the equator. And that's how it just gives you an idea in terms of where they start and then how they migrate and what are the areas that they are in risk from these events. This is how they develop. They develop off the coast of Africa, again in the northern hemisphere for ourselves. There is a term, we call it Scirocco. It's very hot, intense heat that really starts developing in central Africa and that big Sahara. And then as they begin to migrate into west, when they get onto the coast, all of a sudden the differential in the thermal properties, they start beginning to create the low depression, and then they begin to spin. And then this is how on the upper right-hand side, this process starts. And later on, they continue to migrate west. When they get to the Americas, and then they hit that central area, and then look at that spaghetti, and then it's a guesswork. Where is it coming, how big it is, where it's going, how fast it's moving, so on and so forth. Science is getting better and better to really predict those, but it's still not an exact science. I wanted to give you a little more kind of a close look at the hurricanes. Once they start develop, there you can see the eye, and you can see the counterclockwise motion. When you are on the east side of the hurricane, winds tend to be from the south to north, and then when you are on the west side, they tend to be from north to south. And then as they move, sometimes they move very slowly, particularly when they are over water. The minute they come in and hit the coast, also now the differential in temperature and the pressure between the coast and the land, and then they begin to accelerate. This gives you a little bit of an idea. We have a scale, we call it the Saffir-Simpson scale, which classifies the different categories of hurricanes, so we know how we need to prepare for it and so on and so forth, what the intensity is going to be, and then we can forecast what the potential risk or damage is going to be from these hurricanes. Category 5s are usually nasty hurricanes. They are more than 155 miles per hour sustained wind. And then of course you go all the way down to Category 1. It's important to really understand that only 6 Category 5 hurricanes have occurred in the Western Atlantic or the Gulf of Mexico since 1969. But with global warming and sea level rise, our predictions are we're going to get more significant, bigger and nastier hurricanes in the future. Although these are big disasters, but that's, you know, icing on the cake for engineers. I hate to say this, but because we prepare for it, we like to really increase our resiliency, and this is what we want to talk about in terms of how we can take our shorelines that they are vulnerable to erosion and all that stuff, and then through various categories, hybrid systems or living shorelines or typical structural engineering, so on and so forth, we can prepare for it. We are better if we prepare for it rather than go back after an event and try to really fix the damage. Now, nor'easters, they are unique to the Northeast and New England. That's why they are called nor'easters. They are just as nasty as hurricanes, and if not more. Gives you an idea, again, the characteristics of the nor'easters. They can happen any time in the year, although they are really common more in September or April. They are massive cyclonic storms. Two fronts, when they collide together, usually begin to generate the event. Cold air from Atlantic and warm air from the Gulf Stream. They travel inland and northward, generate strong northeasterly winds, generate hurricane force winds, create coastal flooding, create coastal erosion and inundation, can spin occasional tornadoes, create massive coastal flooding, create blizzard conditions in the winter, and they introduce frigid temperature in the winter as well. Here's one that we got last year, nor'easter March 2014. Look at it. It's massive, very powerful. We get a lot more of those as a direct hit than we really get hurricanes. Effects of hurricane and nor'easter on the coast. I'm going to just go through this very quickly. Direct effects on the coastal region. Shoreline inundation, sediment budget change, tidal surge, storm currents, affect local salinity temporarily. change in ecosystem, damaging wind, loss in beach of barrier beaches, and shoreline erosion and overwash, wetland damage, loss of property, economic impact, impact on marine commerce, and increase in the level of badness. And it's not only today, it's predicted into more severe events in the future. So we all need to work together, and we can't continue to proceed as me or you or us. All we have to put our heads together, us, we're going to be able to really meet the challenge that's ahead of us for the next generation. So make sure that we are getting ready and we're not just chasing our tail and trying to fix things after these events happen. When I was younger, I used to love to chase storms. Everybody used to run away from coastal storms. I used to run into them with my camera. I want to take some pictures. This is in Quincy. I took that picture. And I got soaking wet that day. And I loved it. Man, it was just beautiful. See all these waves coming in and just going up and down. That, I didn't take that one. Just wanted to demonstrate to you the type of waves and then things we have. We have spilling waves, collapsing waves, plunging waves, and surging waves. The collapsing waves and spilling waves, they don't release as high as this energy versus compared to the plunging waves and surging waves. Now you can tell that those two buggers down there are a very high energy. I mean, try to imagine you are there, they just tear everything apart. Various types of coastal waves. It's like Jennifer explained earlier about the fetch and the wind. The wind acts on the water sheet and then begins to develop the waves. When you are in the deep area, you begin to get rotary system of the waves. As the wave energy begins to drive and it gets closer to the coast, then you becomes orbital. And then as you get closer to the shoreline, because of the slope of the shoreline, then the waves, because of the drag coefficient in the bottom, it slows the wave train in the bottom, and the celerity of the wave gets much steeper. And then as they get to the point that they can't really, how would I say that? They can't really sustain themselves, then they break. Once they break, they release that massive energy, and then they create the swash up the beach, and then of course the back. And then that's the most vulnerable area when it comes into erosion. And again, give you some ideas in terms of when they start breaking as they come into shallower water, and that's how we begin to get erosional forces. Here's a typical cross-section. When we begin to really forecast a nor'easter or a hurricane and things like that, we need to really account for all the components of what's going to happen that day. In this particular things, I took it at mean low water. Then you get the pressure setup. The pressure is when you have a low pressure under those cyclonic effects, it begins to kind of lift the water upward. Then you got the wind setup, wind's coming in, trying to pile the waves towards the shore and not allowing the wave to retreat. So you get an additional height for that. Then you get the wave set up, and then you get the wave crest on top of it. And you begin to get the wave run up. Now imagine this happens at low tide. When usually happen, we get less destructive forces on our assets around the coastal area. But when those happen during the high tide, then we are in trouble. Again, a little bit of an idea in terms of how the process works. We have a basic formula. We say waves normally break in the nearshore zone when forward velocity begins to be affected by bottom friction and the depth of the water equal to about 1.28 times the height of the given wave. When it gets to that point, it can't really support itself anymore, and it starts breaking and unloading its energy. And here's again a little more kind of a nice vignette. It shows you from the wave height all the way from deep ocean water. You get into the wavelengths and then crest. Wavelengths, by the way, is the distance between the two peaks or the two troughs. And the wave height is the differential between the peak and the lower. All these are just basic physical dynamics that we account for when we begin to assess the wave energy and its destructive power or its healing power. I wanted to give you an idea. Not all waves are bad. During the winter seaon, usually you get the waves, and then they begin to really, where is that little bugger in here? During the winter time, the massive big waves come in, and they begin to chew at the dunes that we have. And then they take the sand and they bring it back, and if we are lucky, we can create an offshore sandbar. If that sandbar gets disappeared and it goes beyond the influence of the surf zone, then we lose it. It doesn't come back. However, if we create that sandbar in the winter time, and then we have in the summertime or in a better season, we can healing waves. That low waves come in, they take that sandbar and bring it back onto the beach, and then they build it. When we do littoral transport or net drift in the sand zone, we go back and then we take transects at the same area on various seasons, because sand sometimes move this direction or that direction. If we want to take a look at the health in given beach, we want to determine whether it's eroding or accreting or whatever, you have to go back and then do a recurrent survey for the area, and then you have to compete the net transport and to figure out whether it's going to the right or it's going to the left, and then you come up with the right solution. And just I wanted to give you an idea, as the waves come in and they begin to approach the coastal area, because of the topography of down beneath, they create longshore transport. As you can see, sand movement in this direction, because when the waves come in, it creates a movement in that direction, and then sand begins to move in that area. Similarly, all these, and then that's why you see the old groins that we have built throughout the entire country, so coastal areas, so we can trap the movement of the sand. Sand is a good medium, really, to give us protection against wave action. It's one of the best measures that we have with minimum impact on the ecosystem to be able to really employ protection throughout. I want to just mention a couple of things for you. We have better tools today than 40 years ago when I started my career, when we used to rub two sticks together to make fire. We have better tools these days. We have AdCirc advanced models. We have ST-Wave, which the Army Corps of Engineers developed. Coastal hazard analysis, so we can go ahead and then create modeling and then begin to assess the various potential high energy area, so we can decide what are the most important areas for us to begin to concentrate on as we get ready to the next wave action or elements. Now we need to talk about a little bit about the tides. This is a nice way to really describe why tides occur, how they occur, what is the influence on the tides. The tide essentially is a function of gravitational pull between the sun and the moon. When they are aligned together, we get maximum spring tides. When they are 90 degrees to each other, we get the minimum tides. And then when they go in the opposite direction, again, we get the maximum tide. And usually this goes with the phase of the moons. Usually you get the high tide, we call them a spring tide or neap tides, depending when you are on the new phase of the moon, or the full moon, or the new star of the moon. So it gives you an idea. All this information, by the way, it's going to be available, correct? Yeah, that's I'm going to move on. Coastal erosion in a high energy area. You can appreciate what a wave energy can do. The reason I put this in there, we can't do living shorelines in those kind of a high energy area. So we have to be specific, and we're going to be site specific in terms of where we can do those. Here's what storms, nor'easters, and then Sandy has done. Just give you an idea in terms of the power of these things. Wonderful stuff. Engineers love these things in the old days. This was coastal engineering 20, 30 years ago. Now we're changing our attitudes, our mind, by working with our ecological colleagues. Some of the stuff we did, though, it's good. It works. Here it is. If those aren't there, that beach would have gone. By creating a little bit of offshore breakwater, you create nice tambolos, you make the depth of the beach wide enough, and that gives you the best protection against the wind and waves. Now we are going to talk about living shoreline. These are little examples in terms of how we can do. This is kind of a moderate energy. This is low energy area. And Jennifer talked about the hybrid system, which is a sill, which gives you the protection in the lee side of that sill to be able to establish the living shoreline and then grow it and maintain it. Again, a couple of quick pictures. Jennifer talked about that, and then Laura is going to concentrate a little more about this subject. Managing complex coastal processes. It's not simple anymore. Look at that. We define the problem, establish the context, identify the relevant and analysis, and appraise and do options, and then we go in full circle. We have to consider all of this as we begin to really address given problem within our coastal area. Again, I want to warm your hearts today. It's a cold day outside. This beautiful shot, I took that from Gayhead. I love it. I live on the water, and even with 10 feet of sea level rise, I'm not giving it up. Thank you, and we have questions.